Okay, to be able to talk about remainder theorem, I need to review a little bit about what I taught you about division of polynomials. So let's observe first. Make an observation. Px is given as x cubed plus 5x squared minus 11x plus 3. Okay, so now I want to divide it by x minus 2. We call it polynomial, and x minus 2 is divisor. Okay, my divisor is a linear x minus 2. So when you do that, you are going to have your quotient, and then your remainder divided by your divisor. So finding this qx, the whole process of finding qx is called polynomial long division. So we have discussed how to divide yesterday, and that's why we have to learn that first to talk about remainder theorem. When you do that, you have, I will make it fast, so 7x squared minus 11x, and then multiply 7x, so 7x squared minus 14x, everything gone, and then 3x plus 3, so you also multiply 3x minus 6, the same slide, only thing left over is 9. So this is called the remainder, and then what do you call this one? This is called your quotient, q or qx, okay? So I am going to just replace these numbers by what we actually found. So quotient first, x squared plus 7x plus 3 plus remainder 9. So when you observe the whole process, you can rewrite as px is x minus 2, your divisor, multiplied by your quotient, okay, plus 9, your remainder. Now, you don't have zeros here. It could have been so much nicer if x minus 2 is a factor, which means 2 is your 0, and it's very clean without any remainder. That's very ideal. But it has a remainder. It's a little bit messy, but that's what it is. So what we can say is that if we plug in x is 2, then 0 times your quotient, so basically 0, plus 9, it's just 9. Okay, so basically this whole observation can be generalized with general terms. So what you can say nicely, making a conclusion, is that when a polynomial px is divided by x minus k, so it's your divisor times your quotient, and then you have a remainder, then when you plug k instead of x, you have your remainder. That is the remainder theorem. Okay, so not very complicated theorem, but it can be very useful when you solve problems. So, example 4, okay. Example 4. I am going to give you maybe 2 examples, and then you can try by yourself. I will start with the first one. Okay, px is given as the multiple of 2 quadratic. And then you have a remainder. Okay, so basically x squared minus 3x plus 7 is not a factor because you have this redundant remainder there. But px has 2 and negative 1 as zeros. And then the given information, another information is, oh, sorry, it's not zeros. Sorry about that. When you have x is 2, then you have a remainder is 29. When you have a p negative 1, which means negative 1 is your x, you have a negative 16 as your remainder. Okay, so what your role is, find your remainder in terms of ax plus b. So now your remainder is not a constant term, it is ax plus b. Okay, that one. So what does that mean? When you plug 2, you have 2 squared minus 6 plus 7 multiplied by 2 squared plus 2 minus 1 plus ax plus b. So it's going to be 2x plus b, which is 29. And then when you plug negative 1 instead of x, what do you have? You have 1 plus 3 plus 7, 1 minus 1 minus 1, and then you have negative, sorry, here, a, not x. Okay, minus a plus b is negative 16. So you solve that, this becomes 4 minus 6 plus 7 is 5, so 5 times 5. So 5 plus 2a plus b is 29, and then you have negative 11 minus a plus b is negative 16. Okay, shall we do simultaneous equation or system of equation, whatever you're familiar with? I want to make it simpler, so this is 25. Can I just simplify it as, instead of having the constant terms on the left side, 2a plus b is 4, negative a plus b, I move negative 11, or I add 11 on both sides, so I have negative 5. So when you subtract it, it's 3a equals 9, so you have an answer. A is 3, thus negative 3 plus b is negative 5, so you have negative 2 for b. Okay, so your answer, Rx, the remainder, is 3x minus 2. Right, that was example. Let's work on another example to use remainder theorem. Example 5. Okay. X plus 3 is a vector of px. Px is x cubed plus ax squared minus 7x plus 6. Find a and all factors. Okay, that's one of them. And then I give you just head start. Plug negative 3 instead of x, because x plus 3 is a factor. Then what happens is that it's basically 0, because we talked about it. Factor right here, negative 3 gives you 0. So it's a very nice clue that we can work with. So this is 0, basically what it is. Negative 3 cubed plus a, negative 3 squared minus 7, negative 3 plus 6. So instead of x, I plug in negative 3's above. And then what do I have? Negative 27 plus 9a plus 27, because 21 plus 6 is 27, which is 9a is 0, right? So a is 0. You figured out a. And then how do you find out all the possible vectors here? Well, px is now, it's cleaner. X cubed, a is 0, so negative 7x plus 6. And then you know that one of the factors is given as x plus 3. So you just have to find here. What would that be? X squared minus 7x cubed minus 7x plus 6 divided by x plus 3. So x squared, x cubed plus 3x squared minus x squared minus 7x, just carry down. And then you multiply negative 3x to make it negative 3x squared. Then negative 9x. What do you have? You cancel. So you have 2x plus 6. Ooh, now it's clean. There's no remainder. It's if you multiply 2x plus 3, you have 2x plus 6 and 0. So, so I am going to just copy and paste. X squared minus 3x plus 2 can be factor one more time. X minus 2 times x minus 1. So what are your zeros here? The first 0 is negative 3. The second one is 2. The third one is 1. Okay, you have 3 zeros. Agree?